I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll briefly discuss about the probabilistic classifier, namely naive-Bayes model. This naive-Bayes is a probabilistic classification algorithm based on Bayes theorem. This we have seen it in the previous lecture, which assumes that features are conditionally independent given the class label. Despite the strong assumption of independence, Naive-Bayes performs remarkably well in many real-world applications such as spam filtering, sentiment analysis, and medical diagnosis. It calculates the probability of a class based on the likelihood of features and prior probabilities, making it efficient for large datasets. The model is easy to implement, requires minimal training data, and works effectively even when the assumption of feature independence is not strictly true. So, we'll see the detailed discussion in the future slides. So first we'll see the introduction to naive-Bayes algorithm. The naive-Bayes model is a supervised machine learning. All you should understand, it is not a unsupervised, it is a supervised learning. So this is supervised machine learning algorithm based on Bayes theorem. It predicts class labels by calculating the posterior probability for each class and selecting the one with the highest probability. The model makes a simplifying assumption that all features are independent of each other, given the class label. Despite this naive assumption, naive-Bayes often performs remarkably well in real-world applications, particularly in text classification, spam detection. This is text classification, spam detection, and sentiment analysis. What is Bayes theorem formula? All you know that. The Bayes theorem formula, this we have seen it. It provides the mathematical foundation for naive-Bayes algorithm. The formula is given by probability of A given B is equal to probability of B given A into, this we can write it as like this, probability of B given A into probability of A divided by probability of B. Here this is the division. And the probability of A given B, this is posterior probability. This is probability of B given A is likelihood. And the probability of A is prior probability. And this probability of B is the evidence or marginal likelihood. So one more time I'll tell you the Bayes theorem. This theorem provides the mathematical foundation for naive-Bayes algorithm. The formula is given by probability of P given A, that is probability of A given B is equal to B given A into probability of A divided by probability of B. And this probability of B is the evidence or marginal likelihood. The probability of observing the evidence, this we can call it as. This formula forms the basis for updating the probability of a hypothesis as more evidence becomes available. And why we are calling this as a naive? Why is it called naive? The term naive, here, naive-Bayes we are calling, no? The term naive stems from the strong assumption that all features are independent. All features are independent of each other given the class label. In real world scenarios, this assumption is often unrealistic because Features usually have some degree of correlation. However, this naive assumption greatly simplifies the computation of probabilities and make the model computationally efficient, enabling fast classification, especially in high dimensional data. This is mainly used in the high dimensional data sets. The classification data sets it is used. Next, key assumptions of naive Bayes algorithm. The primary assumption of naive Bayes is that all features contribute independently to the outcome given the class label. Mathematically, if you want to calculate the probability of x1 comma x2 comma xn given c, you can write it as a probability of x1. See, say for example, if you are given with probability of x1 comma x2 comma x3 up to xn, capital Xn, given c, this you can write it as probability of x1 given c into probability of x2 given c, etc. It will go like this. This independence assumption reduces the complexity of model, allowing it to calculate probabilities efficiently even in large data sets with many features. While this assumption may not always hold, the model still tends to perform well practice. Next, how Naive's algorithm works. There are two phases are there, training phase and prediction phase. Naive works into primary phases, namely training phase and prediction phase. The training phase, it calculates the prior probability for each class, and also it calculates the likelihood for feature each feature given in the class. Next, in the it applies it applies the Bayes theorem to compute the posterior probability for each each class, and then it assigns the class label with the highest posterior probability for each class, and assign the class label with the highest posterior probability to the new data point, posterior probability to new data point. This is simple and efficient process allows what naive Bayes to perform classification tasks quickly and accurately. And the mathematical representation of this is given by, as I've said, probability of ck given x. We can write it as a probability of x given ck into, that is multiplication of probability of ck divided by probability of x. This is the mathematical representation. And since probability of x is the constant for each classes, we can write it as probability of c given x is directly proportional to probability of ck into n is equal to 1 to this. We can write it as n is equal to 1 to n, that is I is equal to 1 to n probability of xi given ck. Next, the types of naive Bayes model. We'll see the problem in the later slides. There are three types or there in the naive Bayes model. First model is the Gaussian naive model. This model assumes that continuous features follow a Gaussian, that is normal Gaussian distribution, what we can call it as a normal distribution. It is used when the features are real values. Features are, in this case, features are real valued and continuous. In this case, it is used. Next one is the multi-model naive Bayes. This model is suitable for text classification tasks where features represent word frequencies or word frequencies or counts. It models the occurrence of words. Suppose if you are in the text, words in documentation, occurrence of words in documents. Next, Bernoulli naive Bayes. This is also very, very important algorithm. It is ideal for binary, otherwise we can call it as Boolean feature data. This is used in the binary or Boolean feature data, where each feature can take only two values. What are the two values? It will take only two values, either 0 or 1. Two values, 0 or 1. It is often used in spam filtering and documentation and document classification. So I'll repeat once again. There are three types of Bayes models: Gaussian naive Bayes, multimodal naive Bayes, and Bernoulli's naive Bayes. And the Gaussian naive Bayes assumes that continuous features follow the Gaussian model, that is normal distribution. It is used when the features are real valued and continuous. Multimodal, multinomial Nomial naive Bayes, not multimodal. Multinomial naive Bayes is suitable for text classification tasks where features represent word frequencies or counts. It models the occurrence of words in documents. Next, Bernoulli naive Bayes. It is suitable for the binary classification or ideal for binary or Boolean feature data where each feature can take only two values. What are all the two values? Either 0 or 1. It is often used in spam filtering and document classification. One example we'll see. The example scenario is the consider a classification task where email is classified as spam or not. Spam based on the presence of certain keywords such as free, offer. What are all the features we are using? Free, offer, or win. And the prior probability used in the prior probability that an email is spam or not, it is used for. And the likelihood used in this case is the probability of observing certain words in spam or non spam emails. Next, the prediction. How you are going to predict? Using Bayes theorem, the model calculates the posterior probability and assigns the class with the highest probability. Assign the class with the highest. This approach is widely used in the spam filtering system, mainly in the emails. Spam filtering systems, we are using this naive algorithm. Okay, next we'll move on to the what are the advantages of this naive algorithm. The naive algorithm is known for its simplicity and ease of implementation. This is the first advantage, making it an excellent choice for beginners in machine learning. Next, it is computationally fast and efficient even when working with large data sets, as it calculates probabilities based on feature independence assumptions. The model performs exceptionally well with high dimensional data. This is the main advantage of using this naive algorithm. High dimensional data, it has been used, such as text classification, where many features are involved. Additionally, naive requires less training data compared to other complex models, enabling quick modeling building. It is particularly effective in scenarios where speed and efficiency are essential, making it highly useful for tasks like spam filtering and sentiment analysis. And it has also got some disadvantages. Despite its advantages, the naive-based algorithms suffer from the assumption of feature independence, which rely on rarely holds true in real-world scenarios. This assumption can lead to inaccurate predictions when features are correlated. If it has been correlated, inaccurate predictions only we are getting. Another limitation is that model is sensitive to imbalanced data, Okay, imbalanced data leading to biased predictions. Means what? Inaccurate prediction, first you have to remember. Next limitation, you have to remember it is sensitive to imbalanced data, potentially leading to biased prediction when one class dominates the data sets. Naive Bayes may also perform poorly when complex relationship exists between features and exists between features, as it cannot capture interactions or dependencies. Additionally, it encounters the zero probability problem, where an unseen category in the training result results in zero probability during the classification, which can affect the prediction. So these are all the disadvantages of naive Bayes. The applications of naive Bayes algorithms are: the naive Bayes is widely used in the spam email filtering, where it effectively classifies emails as spam or not based on word frequency and patterns. It also excels in sentiment analysis task, where it determines the sentiment positive, negative, or neutral. Positive, negative, or neutral. It is used of user reviews or social media comments. In document and news categorization, so third application, Naviebase is employed to classify text documents into predefined categories efficiently. In the medical field, if you are taking the medical field, it is used for disease prediction and diagnosis, helping identify possible conditions based on symptoms. Additionally, it plays a crucial role or important role in recommendation systems, offering personalized suggestions based on user preferences and past interactions, mainly in this Amazon, and that is online shopping, etc. And coming into the conclusion, this Naviebase is a simple yet powerful classification algorithm that performs exceptionally well in text classification and NLP tasks. Despite its unrealistic independence assumption, the model often delivers high accuracy in many practical applications. Its efficiency, ease of implementation, and ability to handle large data sets make it popular choice for various machine learning tasks. Hope you everyone understood the basic about this naive Bayes algorithm. We'll solve the problem in the based on this naive Bayes algorithm in the next lecture. Thank you.